Hi everybody, welcome to lecture 29 of Electrical Engineering 331 and in this lecture we will continue to review for the final exam. So let's jump right in it. In example 29.1 you're given a function y of t that looks like this and you're asked to find dy dt. So I think that once you have the formula for the function, then finding the derivative is easy. So the hard part here is to make sure that you have the correct formula for the function itself. And so I encourage you to try to do this on your own. And then after you have an answer that you think is correct, then come back to the video and compare it to what we do here. Okay, so when we look at this function, the first thing we see is we're moving from left to right is this upward slope, and it's a slope of 2. You can see because it rises 2 in a horizontal distance of 1, and it starts at -1, so that's 2r of t plus 1. And then once we get to t equals 0, you see that this takes a sudden jump down by 1 unit. So that's the minus u of t part that we have right here. Now in addition to jumping down, the slope of the graph changes rather dramatically. Instead of being positive 2 as it was there, it now becomes a slope of -1. And so that means that we need to subtract off 3r of t, which you see right here. And then finally, there's one more change of slope here at t equals 1. The slope goes from -1 to 0. So that means we can, which we can achieve by adding r of t minus 1. Now, to me, this seems a little bit complicated, and so it would sure make me feel better if I could check it. And actually, as you know, with these singularity functions, the way that they turn on at different points, it's rather easy to check these. So let's go ahead and check this and see if it looks like it's correct. So the first thing we observe is that the function that will turn on the first is this 2r of t plus 1. That turns on at t equals -1. U of t and r of t turn on at t equals 0, and then r of t minus 1 turns on at t equals +1. So for t less than -1, nothing is turned on, and we have y of t equals 0. Then once we get between -1 and 0, there's just this one term that it has been turned on, and so the function will be equal to 2 times t plus 1. Because that's what r of t plus 1 is equal to once t plus 1 is greater than 0, which of course will be the case if t is between -1 and 0. So that's all we'll have for -1 is less than t is less than 0. But then as we then continue to move and we get between 0 and 1, now 2 more terms will turn on. So we still have the 2 times t plus 1 from the previous step. That's still turned on. But now we also turn on the -u of t, which gives us -1, and -3r of t gives us -3t. And that's valid for t between 0 and 1. And then finally, once t is greater than 1, the last term will turn on as well. And so we'll have down here everything we had from the previous step, and we'll also have plus t minus 1 from this r of t minus 1. So now if you simplify each one of these expressions, which I'll let you do because this is just algebra, you'll come up with the final answer that looks like this. And you can see that that exactly matches what we have up here. Y of t is equal to 0. If t is less than -1, that's good, so I put a check mark there. It's equal to 2t plus 2 if t is between -1 and 0. And you can see that that's right, because 2t plus 2, when you're at -1, that would give you 2 times -1 plus 2, or -2 plus 2 is 0, so it agrees there. And when you're at t equals 0, it gives you 2 times 0 plus 2, which is 2. And so it agrees at the endpoints, and it's a linear function, so it agrees everywhere. So the second expression also gets a red check mark. Now between 0 and 1, it says it's equal to -t plus 1. Once again, we can check this. This is a linear expression. We can check it at the two endpoints. -0 plus 1 is 1, so it agrees here at t equals 0. And -1 plus 1 is 0, so it agrees at t equals 1. And so that's correct as well, and that gets a check. And then obviously, for t greater than 1 is equal to 0. So that gets a check as well. And this expression for y of t that we have right up here, this expression is then correct. And so now we'll just bring that same expression down here, and we're ready now to finally finish this problem. Remember, what we wanted to do was actually to find dy dt, and now it's a simple matter to take the derivative everywhere. So we get 2u of t plus 1 minus delta of t minus 3u of t plus u of t minus 1. And that's the way we do this first example. Now let's look at example 29.2. What we have here in this problem is two systems. We have a system A, which has this input-output equation, and system B, which has a similar input-output equation. In fact, on the left-hand side, the two equations are exactly the same. But on the right-hand side, they differ. For system A, the right-hand side is only x of t, but for system B, the right-hand side is dx dt minus 3x of t. And so we're told that the impulse response of system A is HA of t, and the impulse response of system B is HB of t. And then we're also told that HA of t is known to be e to the minus 4tu of t. So what is HB of t? Well, because of the similarity of these equations, we can say that the impulse response of this system here is just dHA dt minus 3HA of t, because of the relationship between this right-hand side and this right-hand side. So that's what we've written here, is that HB of t is dHA dt minus 3HA of t. And so that is ddt of e to the minus 4tu of t minus 3 times e to the minus 4tu of t. And so if we use the product rule, when we take the derivative here, we get the first times the derivative of the second, and then the second times the derivative of the first would give us minus 4e to the minus 4tu of t, and then bring this down minus 3e to the minus 4tu of t. Now remember, when you have a function multiplying the delta function, you can just evaluate this multiplying function at t equals 0. And so e to the minus 4t evaluated at t equals 0 is just 1. And so this first term just becomes delta of t, and then the next two terms we can combine together to get minus 7e to the minus 4t u of t. And that is the impulse response for system B. Now for our third example. In our third example, we are given the step response of a linear time invariant system right here. And we're told that y of t is the response to this x of t here. Okay? And so we want to know, what is y of t? What is the response of the system to this input if this is the response of the system to the unit step input? Okay, well, this problem, you might remember how to do this First of all, let's write an equation for this x of t. And that's easy. It's just equal to u of t minus u of t minus 1. So that means that the response to x of t is the response to u of t, which is y step of t. That's what we mean by y step of t, that is the response to the step function u of t, minus the response to u of t minus 1, which is y step of t minus 1. Okay, so this is a formula for y of t in terms of y step of t. But now we need to find out, well, what is y step of t exactly? Here's the picture for y step of t. Up here, when we put that in terms of a formula, well, going from left to right, we jump up at 0, so that's u of t. And then we start to slope down at t equals 1, and the amount of slope is -1. So that's where we get minus r of t minus 1. And then it flattens out at t equals 2. And so that's where we get the plus r of t minus 2. So y step of t is u of t minus r of t minus 1 plus r of t minus 2. And our desired function y of t is equal to that minus that, but evaluated at t equals t minus 1. And so that's exactly what we'll do then. Here, these first three terms represent y step of t, and then we want to subtract that from, we want to subtract from that y step of t minus 1. So here in the brackets, I have exactly the same as I have up here, except that everywhere there's a t, I've replaced it by t minus 1. So u of t becomes u of t minus 1. R of t minus 1 becomes r of t minus 1 minus 1, or r of t minus 2. And r of t minus 2 becomes r of t minus 1 minus 2, or r of t minus 3. And so then when I multiply through by this negative sign, this gives me u of t minus r of t minus 1 plus r of t minus 2 minus u of t minus 1 plus r of t minus 2 minus r of t minus 3. And then I'll write down the terms in order in which they turn on. So I have this u of t, that's the one that turns on first. And then at t equals 1, a couple of things turn on here. So I'm going to bring the u of t minus 1 first, and that's just a matter of personal choice. You could have written r of t minus 1 first if you wish, but I just like to, since I already had a unit step, it's sort of convenient to write another unit step. So I brought this one there, and then the minus r of t minus 1 I wrote there. And then notice that this r of t minus 2 combines with this r of t minus 2 to give 2r of t minus 2. And then finally, the minus r of t minus 3 comes down like this. And now let's graph this function. Okay, at t equals 0, it jumps up by 1 unit. So that's how we get that. And then it will stay at that level until we get to t equals 1. And at t equals 1, it's going to jump down 1 unit. But also at t equals 1, it's going to start to slope down with a slope of -1 because of this. So that's, you see this sloping down with a slope of -1. And then at t equals 2, we're going to change that slope by +2. So it goes from -1 to -1 plus a +2, which is +1. And so the slope here is +1. And then finally, we're going to flatten that out by subtracting the r of t minus 3 to get this. And so the response y of t to this input x of t is given by this graph here. Now we have two more examples in this lecture, And the best example is 29.4 and 29.5. And as you see here, I say that 29.4 is very important. And then for 29.5, I say very, very important. So please do pay very careful attention to these two problems, because they get really at the heart of a lot of what we're doing in this course. So pay close attention. Okay. So in 29.4, we want to evaluate a convolution. We have y of t is equal to h of t convolved with x of t, where h and x are both the same function, e to the minus 3t u of t. Now, our old way of doing a problem like this would be just the brute force method of writing down the definition for the integral, the convolution integral. And since h and x here are the very same function, it doesn't matter if we write it down as h of t times x of t minus tau or x of tau times h of t minus tau, because obviously either way we will get exactly the same integrand. So when we go ahead and substitute for h and for x, this is what we get. And this is one of these cases where we have to be very careful. So let's look at it just step by step. Well, one thing we notice right away is that from this term right here, we have e to the negative 3t. Now keep in mind, we are integrating with respect to tau, not with respect to t. So that e to the minus 3t can come outside of the integral like this. Notice also that we have e to the minus 3 tau here, and e to the negative 3 times negative tau, or e to the positive 3 tau there. So when you multiply those together, you just get 1. So after taking that e to the minus 3t out and observing that e to the minus 3 tau times e to the 3 tau is 1, all we're left with is this integral. Now, this is one of these integrals where we have to be very careful about what these u functions, these unit step functions, do. So I think that the way that I would suggest approaching it is like this. We know, let's look at this unit step function first. We know that when tau, this integral, tau is going from negative infinity to infinity. But when tau gets greater than t, the argument of this unit step will become a negative number, which means that that unit step will give us 0, which means that we don't have any more contribution to the integral. So that means that we don't have to let tau go all the way to infinity. We can just stop tau when it gets to t, because after that, there's going to be no more contribution to the integral. So if we change the upper limit of the integral from infinity to t, then we have accounted for the presence of this term, because of course it's equal to 1 for tau less than t, and it's equal to 0 for tau greater than t. So then we can take that out. So now we have just one unit step function in the integrand. And you might remember we've done some problems like this, but I think the easiest way to reason it is the following. Tau is now going from negative infinity to t. So think about it like this. If t is negative, if t is some negative number, then this is never going to turn on, because u is non-zero only if its argument is greater than 0. But if t is a negative number, then tau will never get to be a positive number. So whatever we're going to get here had better be 0 whenever t is negative. Okay? On the other hand, if t is positive, then we really don't have to worry when tau is in the range from negative infinity up to 0, because, again, when tau is in that range, the integrand is just 0. So this means then that the integral is the integral 0 to t, and in that range, when tau is between 0 and t, This function right here is just equal to 1, so that's why it's disappeared. And the u of t out here serves the purpose of making sure that we know that this expression right here is correct only when t is greater than 0. If t is less than 0, then we just multiply by 0 here and 0 out everything. So that's how we can think about the way to simplify this integral. And then once we get it into that form, we know that the integral of d tau is tau, and our limits are 0 to t. And so this becomes e to the minus 3t times t minus 0 times u of t. And so our final answer is that the convolution is equal to t e to the minus 3t u of t. Now, that's not the worst problem in the world that we've just done, but it certainly is a little tedious, and there's certainly, I think, a probability, certainly a non-zero probability of making some kind of a little error up here. So let's now look at a new way of doing this problem, which is so much easier, as you will see. So again, what we want to do is we have x of t and h of t are both equal to e to the minus 3t u of t. We want to know the convolution of those two. Well, the convolution, when you convolve, you can look this up in your table of Laplace transforms. The Laplace transform of the convolution of two signals is simply the product of their Laplace transforms. So that means that if we take the inverse Laplace transform of each side, then it says that the convolution is just the inverse Laplace transform of h of s times x of s. Well, h of s, if this is h of t, then h of s is 1 over s plus 3, x of s is 1 over s plus 3, and so we have the inverse Laplace transform of 1 over s plus 3 squared, and we look in the table, and that's t e to the minus 3t u of t, and we are done. So that is just so much quicker and easier than what we did above, and not only that, but it is much less error prone. So definitely make sure that you understand this idea. And actually the next problem is just sort of an elaboration on that idea. So let's look at it. And really, I just emphasize very strongly, be absolutely sure that you understand these two examples. Okay. So now we're going to have another problem. It says a system has the input-output equation dy dt plus 2y of t is equal to 3 dx dt plus 4x of t. What is the unit step response of this system? Okay, now as I say, there are several ways that we might have done this problem in the past. One way would have been, you might remember that we had a rather involved procedure, a recipe, a multi-step recipe for finding the impulse response of a system. So that's one thing we could have done. We could have found the impulse response of this system. And then once we had the impulse response, we could have, we could have convolved it with the unit step function in order to get the unit step response. That's one thing we could have done. Or another thing we could have done is we could have just said, well, if we have the impulse response, then all we have to do with that is just to integrate it. I'm not talking now about convolving it with the unit step. I'm just saying we could have taken the impulse response and simply integrated it to get the unit step response. Why is that true? Well, because delta of, let's say it like this, u of t is the integral from negative infinity to t of delta of tau. So the response to u of t is the integral from negative infinity to t of the response to delta of tau, which is the impulse response, h of tau. So that's what I say. We could have just integrated, we could have used our multi-step procedure that we found before to find h of t, the impulse response of this system, and then we could have integrated h of tau d tau from negative infinity to t to get the unit step response. So that's two different ways that we could have done this problem. And another way we could have done it would have been to have substitute in u of t for x of t here at the beginning. And we could have, that would have given us some value here on the right-hand side. And then we could have solved that differential equation using the multi-step procedure. So that's three different, they're not vastly different, but three different ways that we could have done this problem. But each one is, it's fairly tedious. And so now let's look at our new way. The new way is so much easier. That's why I didn't even write out all the details of those old ways, because they're really tedious. And let's just see how easy this is, the new way. So what we're going to do is we're going to take the Laplace transform of both sides of this equation, and we get sy of s plus 2y of s is 3s x of s plus 4x of s. And so if we group everything together, then on the left-hand side we have s plus 2 times y of s, and on the right-hand side 3s plus 4 times x of s. And therefore h of s, the transfer function of the system, which is equal to y of s divided by x of s, is just 3s plus 4 over s plus 2. That's the transfer function of this system. Now remember, what we're asked for is the unit step response. And so the unit step response, well, it's the response to the unit step, which is the impulse response convolved with u of t. But as we said in our previous problem, that convolution is just the inverse Laplace transform of the product of the Laplace transforms of those two functions. So we have h of s times u of s. Well, h of s, we've just concluded, is 3s plus 4 over s plus 2. U of s, we know from the table, is 1 over s. And so this is, when we multiply that together, is 3s plus 4 over s times s plus 2. And if we want to get the inverse Laplace transform of that, then we're going to use the Heaviside method. That's the easiest way. So we write it as a over s plus b over s plus 2. And of course, a then will be equal to 3s plus 4 over s plus 2, evaluated at s equals 0, which is 2. And b will be 3s plus 4 over s, evaluated at s equals negative 2, which would be negative 2 over negative 2, which is 1. And so therefore, the y step of t is the inverse Laplace transform of this 2 over s plus 1 over s plus 2. And we know that that then means that y step of t is 2u of t plus e to the minus 2t u of t. And that is it. So absolutely, positively, again, make sure you understand how to do problems. I certainly want you to be able to do all of them, but absolutely, positively make sure you understand example 29.4 and 29.5, the new ways. Make sure you understand those for sure. So I think that should prepare you for test 29, and so good luck.